Okay, so now we are talking about simple molecules, but that are made up of different atoms. We're going to start off with methane. The diagrams are pretty easy. They have drawn one atom of hydrogen. They have written a 4 behind it to make sure that you understand there are 4 atoms of hydrogen in total, 1 atom of carbon. Remember, though they are putting electronic configuration for all the whole atom, for all the shells, but they're only drawing the valence shell. And that's actually what we require from the student. In paper, you don't even need to do this. It's not asked in exam. If you do this as a single step, this as the second step, this as the third step, that's about it. You don't need to draw these either, right? And you don't need to write any of this, okay? So that's about it. That's usually asked in exams for 3 marks. 3 steps, 3 marks. Sometimes they do give it for 2 marks, but most of the time, 3 marks. Now, you can easily understand carbon has 4 electrons in its outermost shell, so it bonds with 4 hydrogen atoms, making 4 single covalent bonds, 1, 2, 3, and 4. So that's how carbon attains its octet, completes all 8 electrons in its outermost shell. All the 4 hydrogen atoms attain the duplets, and that's how all of them are stable. Another example with nitrogen. Nitrogen in group 5, there are already 5 electrons in the outermost shell, so it only needs 3, hence 3 hydrogen atoms. So it bonds with 3 hydrogen atoms with 3 single covalent bonds, 1, 2, 3, in completed octet. When that happens, a pair of electrons as lone pairs stays on top of nitrogen. This lone pair is usually depicted over here as well as here in the structure. You need to draw this, right? Showing the lone pair on top of ammonia is a very important part. Sometimes if you don't do that, they cut 1 mark out of your work. So that's important. Remember, if there is 1 lone pair, you show it. If there are 2 lone pairs, you show it. If there are 3 lone pairs, you usually do not show that. And you're going to see the same thing on this page. Moving to the bottom of page number 69, you're going to find out the example water. Oxygen, which is actually in group 6, having 6 electrons in it, outermost shell actually binds with just 2 hydrogen atoms. Sharing 2 electrons in the form of single covalent bonds with 2 hydrogen atoms, it completes its octet, having 2 lone pairs on top of it, which are usually drawn on the structure of water. So it gives you the idea that how water forms. Well, oxygen completes its octet, both our hydrogen atoms complete their duplet, and all of them become stable. We draw 2 lone pairs if there are 2 lone pairs on a structure. For chlorine atom, in the case of hydrogen chloride, it's actually 1 single covalent bond. Chlorine becomes stable by completing its octet. So does hydrogen by completing its duplet. And that's how we have this displayed formula. Remember, you can show it like this. You can show the 3 lone pairs, but we usually do not show 3 lone pairs. So no need to do that. Let's stick with the boundaries. Let's stick what the habit of the book authors are, and actually they adopt those habits to make it clearer and easier for students. Next example is of carbon dioxide. In this case, we are actually having a double bond. Actually, 2 double bonds are there, carbon with each of the oxygen atoms, right? So in this case, it's a pretty specific example. There are 2 double bonds over here and here. There are 2 lone pairs on each oxygen, so are a total of 4 lone pairs in the entire structure. This also has been a past paper example, but a rare one at that. Ethene is also an example of a double bond, a carbon-carbon double bond, 2 carbon atoms, 4 hydrogen atoms. You'll see that they are actually drawing the hydrogen atoms not on top or at sides or at bottom. No, in fact, they're drawing them as diagonals. So try copying the way that book goes with. If the book is using this for 4 bonds or this for 3 bonds, diagonals like this one, though this one is a double bond in this case, and this is not nitrogen, this is carbon atom in this case, right? Or goes with straight bonds on both sides. Whatever the case may be, please try following in the footsteps of the authors. There is a reason why we put diagonals or straight lines, top, bottom, right, left. There's a reason behind it. We do not clear that reason at this level, but still, going in that habit is going to give you a good chance of drawing all the structures correctly. Now, this is the first example in which we have three different atoms: carbon, hydrogen, and oxygen. You do not necessarily need to draw six hydrogen atoms. You can simply draw one and write six before it, one carbon atom and write two before it. And since there is only one oxygen atom, so you do not need to write anything. This is the whole diagram that you get because that's a big structure. This has been a past paper question way too many times. So you have this kind of structure. Now, what I usually ask from my students is to draw it a little bit differently. So what I'm going to do is that I'm going to stop sharing over here. So I always ask my students in case of a second. So in case of three atoms, we have C2H5OH. So it's better to
Sir,
draw
your
C with,
screen is stuck.
it's a little slow at my end too. So I'm drawing C with empty circles, I'm drawing H with crosses, and I'm drawing O with filled circles. It's a little slow at my end too.
Right, sir.
So they're going to appear slowly. I hope by now you can see the whole C2H5OH written. And I'm actually
Yes.
going to wait a little bit. So what happens is that you, since you know and you already have seen the structure like this, okay. So you know that we need to draw carbon like this. So draw it with empty circles. 1, 2, 3, 4. And then another carbon atom. Again, this is supposed to be again empty circle. So 1, 2, 3, 4. Next up is oxygen. So filled circle. All circles are filled now. And then you can go ahead with the crosses. Cross hydrogen, cross hydrogen, cross hydrogen, cross hydrogen, so on and so forth. All the crosses and all the hydrogen atoms. Right? That gives you the idea. So what I ask from my students is to always go with a key at the top left or top right of this kind of question. This key is for the examiner. Of course, that leaves a very good impression. Examiner would instantly understand which symbols are you using for which atoms. But actually, this key is very helpful for students themselves. During the drawing of the structure, they can't just simply change their decision and start using one symbol for another kind of atom. For example, you never draw the key up top. You start off with drawing empty circles for carbon atoms, and there in the middle of the structure, you just think of, no, I should draw crosses with carbon atoms and empty circles for hydrogen. You're going to mess up everything. So having a key up top, make sure that you're going to follow the exact pattern as you draw the key in. So that actually keeps you safe from making mistakes. So yeah, it is for the examiner for a good impression, but it's more for you not to make mistakes. I hope I'm clear with my point. Am I?
Yes, sir. But I
Good.
have a question.
Yeah, go ahead.
For the oxygen, we have to make 6 circles.
Yeah, 6 circles, right? Since there are 6 electrons in the outermost shell of oxygen.
Right. Okay. Thank you,
Okay.
sir.
All right. Now, sometimes examiners or Cambridge does say you can use triangles or you can use squares. Okay. I insist my students not to do that. Both of these shapes may be deteriorated or completely be different shapes when you're in a hurry. So it's better to go with empty circles, filled circles, and crosses. That's about it. Good part about Cambridge, they usually do not tend to give you any structure that consists 4 different atoms. So there you go. We have already drawn a boundary line that at most what you're going to get is a structure with 3 different atoms. Okay. So if I erase it all, actually, I'm going to put it aside and let's get started. Okay, the next example we have over here is CH3 COOH, ethanoic acid, something that is an example from organic chemistry, chapter number 10, but is an important past paper question. Again, you have carbon, you have hydrogen, you have oxygen, and you can give them 3 symbols. So fill circles, empty circles, maybe, or crosses. The structure is something like this: C, C, double O, single bonded O, H, and hydrogen atom with all the carbon atoms, with one of the carbon atoms, of course.
No, I just did it the way you do right now.
Okay. I don't know why it's taking so much time. Well, I hope you get the point, right?
Yes, sir.
Okay. There is another example, though, but let's do it on the book. So I'm going to stop sharing I'm going to close up the whiteboard, and let's do it over here. Much better to do it over here than that slow Microsoft whiteboard. I don't know why it's slow today. Okay, so since we're talking about the ethene has the formula C2H2. Sorry, not ethene. I stand corrected. That's ethine, and it's actually a carbon triple bond carbon with one hydrogen on each side. If I display carbon with empty circles and hydrogens with crosses, then it's pretty easy. We have actually 6 circles in the center of both carbon atoms and a dot cross and a dot cross on the other side with each hydrogen atoms. So there you go. You have both the hydrogen, and every carbon has its octet complete, 6 electrons in the exact center, 2 at the other end. There you go, octet complete. It's an example of a triple bond. It has been used rarely in exams. For if I talk about exams beyond 2014, this was common. After 2014, the previous 8 years, not so common. Clear enough?
Right, sir. Yes.
So yeah, I wanted to go with this example of ethanol or ethanoic acid or ethyne in specific. Let's move forward. I hope you're clear with covalent bonding. So let's move ahead with ionic bonding. All right, ionic compounds. Now, ionic compounds is generally a type of a metal and non-metal. This involves transfer of electron. Usually non-metal gains the electron, which the metal loses. This results in transformation of positive and negative ions. Positive ion is usually formed by a metal after the loss of electron. Negative ion is usually formed by the non-metal after the gain of electron. These oppositely charged electrons then attract each other by electrostatic forces of attraction. Remember, the term electrostatic force of attraction is the attraction between unlike charges, positive with negative and negative with positive. So the electrons involved in the formation of ions are those in the outer shell of atoms. Metal atoms lose their outer electrons to become positive ions. In doing so, they achieve the stable electron arrangement of the nearest noble gas. Same rule as we were following back in covalent bonding. Generally, atoms of non-metals gain electrons to become negative ions. Again, in doing so, they achieve the stable electron arrangement of the nearest noble gas. So the most common example actually is sodium chloride, the table salt we eat every day. So let's move to the example at the top of this page. You can see figure 3.23 as the first step. Now, we actually use arrows in this case. In the arrow, the head represents the atom which is about to gain the electron, usually the non-metals. The tail represents the atom that is about to lose the electron, usually the metal. And the arrow is literally drawn to show where the electron is going to go from which position to which position. Now, this results in formation of a positive ion for the metal. So the metal is written simply with brackets and positive outside. If it loses 1 electron, it's going to form a positive 1 ion. For example, this converts into plus. If it's going to lose 2 electrons, that's pretty simple. It's going to form a 2 positive ion. And if it is going to lose 3 electrons, it is going to form a 3 positive ion. On the other hand, if it's going to gain 1 electron, it's going to form a negative ion. It's going to gain 2 electrons, it's going to form a negative 2 ion. If it's going to gain 3 electrons, it's going to form a negative 3 ions. So it's actually loss of electron or loss of 2 electrons or loss of 3 electrons that results in +1, +2, or +3. It's the gain of an electron or gain of 2 electrons or gain of 3 electrons in case of negative, -2, and -3 ions, respectively. And that you can see in the structure of chloride. Chlorine actually has 7 electrons in the outermost shell, which are shown with 7 dots. But there is a cross. This cross represents that this electron is coming from another atom. This does not originally belong to chlorine. And since it has an extra electron, there is a negative charge up top outside the bracket. This is to show that the charge is for the entire chloride ion, not for any specific shell or part of atom. If we look at the structure of sodium and the structure of chlorine in separate diagrams, figure 3.24 actually clarifies what happens to sodium. Now, sodium has an electronic configuration of 281, which means there are a total of 11 electrons in its shell. 2 electrons in the first shell, 8 electrons in the second shell, 1 electron in the third shell. 1 electron is present in the outermost shell, and it is actually lost. Okay, we can't draw the arrow in this case over here. It is actually lost, so it's just left with 2 shells. 2 electrons in the first shell, 8 electrons in the second shell, and now it's not sodium atom anymore. It's a sodium positive ion, Na positive. So if I keep the same example and if I move forward with figure 3.25, you're going to notice that chlorine actually had the electronic configuration of 287, having a total of 17 electrons, 2 in the first shell, 8 in the second shell, and 7 electrons in the outermost shell. Now, gaining 1 electron from sodium actually helped it to be converted into chloride ion, Cl negative, having the configuration of 288, which is actually the nearest noble gas configuration. If we look at the configuration of Na positive ion, you're going to see that it's the configuration of neon. If we look at the configuration of Cl negative ion, you're going to see that it's the configuration of argon. Neon was actually the nearest noble gas to sodium, and argon was actually the nearest noble gas to chlorine. How? Let's take a look at the periodic table and understand what I'm trying to say. Since if you look at the periodic table, you'll understand what I'm talking about. So we're going to go a few pages back. I guess on page number 56, we have the periodic table. So at the bottom of page number 56, when we look at the table, this is page number 56, notice sodium is the very first element in period number 3. This is sodium. If I go back one step, upon losing just 1 electron, we have neon. Neon is the 10th element of the periodic table, sodium is the 11th. That's how close they are. In case of chlorine, that's right over here, the yellow portion. It's the 17th atom in the periodic table. And right next to it, after the gain of just 1 electron, we have argon. So sodium loses 1 electron, attains the nearest noble gas configuration of neon, which is supposed to be 2,8. And chlorine gains that one specific electron and attains the nearest noble gas configuration of argon, which is 288. There are 2 8s in this configuration. So that's how they attain the nearest noble gas configuration and become stable themselves. But in doing so, what happened? What happened was that they were converted into ions. Now, once they're converted into ions, sodium, after the loss of electron, gains a positive charge. Chlorine, after the gain of an electron, gains a negative charge and becomes a chloride ion. Now, they both have charges on them, opposite charges, if I might say, and that is the reason of their electrostatic forces of attraction. They come close, they attract one another very strongly, and they form an ionic lattice. Let's move on to the next page, page number 72, to take a look at the ionic lattice they're going to form. And there you go, figure 3.27. You can see an ionic lattice. There are positive ions and the negative ions, and they are in an alternate arrangement so that every positive ion faces negative ions and every negative ion faces positive ions. This is a huge structure. Lattices are big. They extend in all 3 dimensions. So much so that really depends upon the size of the particle itself. Each ion is surrounded by a whole set of opposite charges. For example, if I have to show this way, Na positive is surrounded by Cl negative, top, bottom, right, left, one in front of it, and one at back of it, in all 3 dimensions. Remember, 2 dimensions are shown by x and y axis, the opposite x, the opposite y. 3 dimensions are shown by z axis included. So this is x, this is minus x, this is y, this is minus y, something you might have studied in maths as well. This is z, and this is minus z. So these are the six positions. If Na positive is present in the center, all six positions are actually covered by chloride ion. So the same goes for actually the chloride ions. If the chloride ion is in the center, the positive ions are top, bottom, right, left, front, back. So this huge lattice is formed. And this lattice has very strong electrostatic forces from all sides. Imagine a positive ion in the center is being attracted with all of the negative ions, or a negative ion in center being attracted by all of the positive ions. So there are so many attractive forces that ionic compounds tend to be solid at room temperature. Some features: metal atoms always lose electrons. They always form positive ions. Most of the time, the number of positive charges in a metal ion are equal to the number of electrons lost, plus one, plus two, plus three. In the similar way, respectively, non-metal ions, with the exception of hydrogen, tend to gain electrons to become negative ions. The number of negative ions in a non-metal ion is equal to the number of electrons gained, minus one, minus two, or minus three, respectively. Again, now, in both cases, the ion form have a more stable electron arrangement, usually that of the nearest noble gas. That's why they are more stable. Ionic bond, which is also known as electrovalent bond, results from the attraction between oppositely charged ions, which we call electrostatic force of attraction. Now, since ionic compounds are usually considered for examples, this is another example. Magnesium oxide is an example of magnesium losing two electrons to oxygen. Both gain nearest noble gas configuration. You can write the positive ion simply, and you can write the negative ion in a proper circle. Now, we do not mention the whole positive ion since it loses electrons, and the shell after the valence shell, I mean inner shell after the valence shell, okay, does not need to be shown. However, we do show the negative ion. Do you know why do we always show the negative ion? That's because it has two different kinds of electrons in it. And that's where the students sometimes, in a haste, make mistake. It cannot be all dots. It cannot be all crosses. It has to be a mixture of dots and crosses. Dots, if showing the original number of electrons, crosses would be the number of electrons gained, or vice versa. So there are six dots showing oxygen is present in group six and having six electrons in its outermost shell. There are two crosses showing that the two electrons originally belong to magnesium in this case and has been gained by oxygen, hence the negative two charge up top. So next one is calcium chloride. Now this one is a little tricky. In this case, one positive ion, one atom actually is becoming a positive ion by losing two of its electrons, but both electrons go to separate atoms of the same kind. Both are chlorine atoms. One electron is good enough to stabilize one chlorine atom, so two electrons go to two different chlorine atoms, and hence we have two negative ions in this case. But the formula is balanced since we are writing CaCl2. So this kind of formula is going to give you a very good idea about the number of atoms. This formula clearly tells us there is one calcium atom, but there are two chlorine atoms in this formula. So these kind of structures are a little tricky. So what I ask from my students is that you can tend to practice Al2O3, since this consists of two aluminum atoms and three oxygen atoms, and aluminum is going to get a charge of +3, oxygen is going to get a charge of -2. It's going to be a little bit of a difficult drawing, but if you can manage it, great. That means you can almost tackle any ionic bonding diagram. Another thing that you can practice is magnesium nitride. It's Mg3N2. It's actually the exact opposite. In this case, magnesium has the +2 charge, and it's the nitride end which has the -3 charge. There are three atoms of magnesium and two of nitrogen in order to balance the whole set of charges. If you practice these two compounds, and if you get to draw them correctly, completely, then I think you can draw any ionic compound for that matter. All right.
Right, sir.
Okay, let's move on. Now, since you know about the ionic compounds, there is something as extra that we need to tell you. Now, ionic compounds such as sodium chloride are solids at room temperature. Their ions arrange themselves in a regular lattice. We call it a giant ionic structure. They actually are held together by huge electrostatic forces of attraction, which are pretty strong. Now, sometimes ionic compounds consist of polyatomic ions. We also call them group ions or compound ions. There are many names, so all of the names are written in bold over here. Simple ions actually consist of one atom only. Polyatomic ions, as the name suggests, poly means many and atomic means atoms. So it's pretty easy to understand. An ion that is made up of many atoms. Take a look at this sulfate. There is one sulfur and four oxygen atoms, a total charge of -2, so a total of five atoms, polyatomic. Nitrate, NO3 negative, four atoms in total, one of nitrogen, three of oxygen, a total charge of negative, or carbonate. So we're gonna take a look at few, and to be honest, there are hardly 7 to 8 polyatomic ions in entire IGCSE course. So it's easier to remember them since you're going to frequently work with them. There are three negative and one positive ion, polyatomic ion drawn over here. Carbonate, CO3 negative 2, nitrate, NO3 negative, sulfate, SO4 negative 2, and finally ammonium, which is the only positive ion over here, NH4 positive. Now, the ions that you're going to encounter in your syllabus or all a decade of past few years papers, you're going to face only these ions, most probably. So simple metal ions, usually all the metals are positive. Hydrogen is the only non-metal that can form a positive ion. Usually all the non-metals are negative. Hydrogen is again unique and can still form a negative ion. There is only one positive polyatomic ion, ammonium. And if you count all of these, you're going to end up in counting six negative ions. So hydroxide, OH negative, nitrate, NO3 negative, hydrogen carbonate, HCO3 negative, sulfate, SO4 negative 2, carbonate, CO3 negative 2, and phosphate, CO4 negative 3. So since there are a total of just seven polyatomic ions, they're easy to remember. And I always ask my students to memorize these. Even if you're going to frequently use them and you're going to automatically memorize them, but it's better to after understand, cram them. It's going to make you quicker with your exam work. Now, the three major types of chemical bonding to summarize were metallic bonding between metals, ionic bonding between a metal and a non-metal, covalent bonding, which was only in between non-metals. So in order to discuss their properties, we first need a big mind map. Let's discuss a big mind map. Now, all the elements are divided into either metals or non-metals. When metals combine, that's metallic bonding. When non-metals combine, it's covalent bonding. Non-metals covalent bonding may give you simple molecules or sometimes giant molecular lattices, which we are still to discuss. We haven't discussed them. Non-metals such as noble gases exist as separate atoms. Metals may exist as giant metallic lattices, but when compounds need to form, metals may combine with non-metals to form ionic bonds, which then result in giant ionic lattices. When non-metals and non-metals combine to form compounds, they may result in covalent bonding, which may result in simple molecules and giant molecular lattices. So non-metals can be elements or non-metals can be compounds. Yeah, that's true. When I use the word elements, I'm talking about these simpler structures, which for which I use the word homatomic, means that are made up of same kind of atoms, right? These ones. And when I talk about simple molecules with non-metals with different non-metals, I'm actually talking about different atoms, like water, like hydrogen chloride, like ammonia, like methane, like all the examples in which you're using more than one kind of atom. So that's what we mean from elements as simple molecules and compounds as simple molecules. We are still to explain the giant molecular lattices. Out of these five in here, we've only explained four so far. So let's just keep this for the upcoming pages. Moving on, something out of chapter number 3 that Cambridge cannot refrain to give in every single year and seasons paper. Take a look at this table, and let me tell you, this comes every single year, every single season as a part of the paper. Beat paper 2, beat paper 4, beat paper 6, MCQs, theory, or alternative to practical. They usually take the properties difference table every single time in their paper. So consider it as the most important part of your chapter 3. Let's clarify. Let's differentiate between them. So what I'm going to do is that I'm going to take point by point and we're going to literally differentiate between ionic compounds and covalent compounds. I'm not going to discuss whole ionic compounds at first and covalent after. So ionic compounds are usually solid at room temperature. That's because they have very strong electrostatic forces of attraction between the differently charged, unlike charged ions, positive and negative ions. On the other hand, simple covalent compounds are usually liquid or gases because they are made up of simple molecules. They have covalent bonds. They don't have any ions in between them. They don't have any electrostatic forces of attraction between them. Now, the ionic compounds have high melting and boiling points. That is due to the strong electrostatic forces of attraction, and we need very large amount of energy to break the bonds. Simple covalent bonds have low melting and boiling points. They're just forces of attraction between the molecules. We don't need much energy to move the molecules further apart. Remember, whenever we melt or boil a covalent compound, we do not break its covalent bonding. But when we melt or boil an ionic compound, we definitely break the ionic bonds. That's a huge difference because of which ionic compounds have high melting and boiling points and simple covalent molecules have very low melting and boiling point. Next up is solubility. Ionic compounds are soluble in water. They're not soluble in organic solvents such as ethanol or methylbenzene. Why? Water is attracted to charges. Since ionic compounds have charged particles, they can easily dissolve in water. However, the exact opposite lies with simple covalent compounds. Most of the simple covalent compounds are only soluble in organic solvents. Very few of them are soluble in water. Since they don't have any ions, they don't have any charged particles, they do not dissolve in water and mostly dissolve in covalent solvents. So the principle like dissolves like can be applied over here. Lastly, ionic compounds do not conduct electricity when they are solid because the ions are not free to move. But they do conduct electricity when they're molten or when they're in their aqueous solution, which means dissolved in water. In that case, ions are free to move and they can actually carry the current or charge. So there are three cases of conductivity in ionic compounds. Remember all three cases. They are not conductors when they're solid. They are conductors when they're molten to liquid form or dissolved in water. Lastly, simple covalent compounds do not conduct electricity. They don't have any ions present in them to carry the current. Since they don't have any ions and they're just in their molecular form, so they do not carry the current. I hope you're clear with all the differences. Are you?
Yes, sir.
Good. I'm going to clear all of this up. Next is 3.5. There are two major things that are covered in this portion, the chemical formulae of compound and naming of compounds. So let's get started. If we talk about formulae of elements, the elements that are present in diatomic form, it's very easy. They're named with their original names, so we don't have to worry. For example, you're going to see diatomic molecules in this case for hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, iodine, sulfur, phosphorus. You're going to see them as simple diatomic molecules. So actually the name of the element and the name of the molecule itself does not change. It's not a problem, right? And there is another kind over here, single atom. This goes for all of noble gases, helium, neon, argon, krypton, xenon, radon, the list goes on. So um, yeah, their formulas are written in the same way. There is not a problem. Most of the metals are also written as alone, though they exist in giant metallic lattices. And then there are giant molecular lattices, which we're going to study later. So moving on, What happens if we are about to write the formula of compound? Now, the compounds are divided into two major categories, ionic and covalent. So when we talk about the formula of ionic compound, we usually go with balancing the charges of all the ions present. In order to do that, there are a couple of prerequisites that we do. So I'm going to first of all go with the prerequisites first. Now, if you look at the name like sodium chloride in the formula FnHCl, the ions are present are Na positive and Cl negative. As you can see, the ratio is 1:1. That's pretty easy. The number of ions present over here are 1 and 1, so the ratio is 1:1. This is 1:4, and since there is one more nitrogen, so 2:4:3. That's pretty easy. Or the ions can be 1:1. Now the ions in this case are 2:1, since there are two potassium ions and there is one sulfate ion, again one calcium ion and two hydrogen carbonate ions, so 1:2. So in this way, we can always come up with a ratio. The ratio was older questions beyond 2016 and 14. Usually the ratio is not considered as a question, but we do explain it for the ease of chapter 6, the most chapter. Apart from that, what we usually ask from our students is to come up with these formula. In order to do that, what I ask from my students is to go to the previous page. Now there are three uh, groups for metals and three groups for non-metals mainly that involve in ionic bonding, and it's pretty easy to come up with the charges that they have. Group 1 has a +1 charge, group 2 has a +2 charge, group 3 has a +3 charge. We're not going to consider group 4 since that's going to form covalent compounds. Group 5 has a -3 charge, 6 has a -2, 7 has -1, and finally this one has a 0 charge. So how do we know how to come up with these numbers? Actually, there is a pet formula to come up with these numbers. Though I write these numbers and ask my students to memorize it, but there are formula mentioned in the book to come up with this number. Let's clear it up. And I'm going to move to the top of page number 77 to clarify the formula. And I'm going to change the formula given in the book a little bit because that's not going to work out clearly for you. So for ionic compounds, let's consider, and I'm not going to use this formula, okay? So for ionic compound, the formula is group number minus 8. This goes for group 5 to 8. And for groups 1 to 4, it's equal to the group number itself. All right. So group 1 has +1 charge, group 2 has +2, group 3 has +3, group 4 has +4. But group 5, if you solve it like this, 5 minus 8 is equal to what? -3, the number I just wrote on the previous table. 6 minus 8 would be equal to what? -2. 7 minus 8 would be equal to what? -1. The numbers I just used in the previous table. So it's a pretty good way to come up with the formula for ionic compound. I hope you get the point, right?
Sir, I don't get this.
Okay. If you get the formula, fine. If you don't get the formula, the numbers I just wrote above the group is a very easy way to know what kind of valency they're going to have. Make sense? If not, I
Right.
can re-explain it. Okay, I can re-explain it. Pretty easy. The point I'm trying to make, let me go back to the table. Okay, let's go back to the values that I wrote. You can simply remember these values: +1, +2, +3, +4, -3, -2, -1, 0. Now you can simply remember these values. Why am I writing this value? This group elements Li, Na, K, they're going to lose one electron only and become a +1 ion. The group 2 elements Be, Mg, Ca, they are every time going to lose 2 electrons and become a +2 ion. The elements of group 3, B, boron, Al, aluminum, Ga, gallium, are usually going to lose 3 electrons and form plus 3. We can safely erase this since these are going to most of the time form covalent compounds and not ions, so you can simply skip it. But if you have to use it, you can use plus 4 for it. That's safe. Now, nitrogen, phosphorus, As, group 5 elements, they're going to gain 3 electrons instead of losing any. Why? Only then, if they gain 1 electron, its configuration, 2 electrons, this configuration, and 3 electrons, finally they'll get to the neon's configuration, right? Or argon's configuration. So that's the point I'm trying to make. The numbers written above is the ion or the charge of the ion they're going to get, because that possibly tells you how many electrons they're going to lose or gain. So oxygen will gain how many electrons? 2 electrons. That's how it's going to end up with a -2 charge. Fluorine, chlorine, bromine, iodine, all of the halogens only need 1 electron to gain. So when they're going to gain 1 electron, they're going to have a -1 charge. So they're always going to form a -1 charged ion. And we also studied it back in the halogens group. Remember?
Yes, sir.
So that's the numbers. You can remember the numbers, and when you get the periodic table, you'd know what kind of ion they're going to form. So let's go with the practice. It says aluminum oxide over here, which means we are going to combine aluminum with oxygen. So where do you see aluminum in this diagram? I mean, which charge do you see up top for aluminum?
+3.
+3, very good. And what charge do you see on top of oxygen?
-2.
-2. So this procedure tells us we are going to use this number below aluminum and use this number below oxygen. Actually, numbers are reversed. But what do? We do not write the signs. We just write the numbers. So Al2O3 is going to be the formula. As easy and simple as that. I think now
Yes.
it's making much more sense, right?
Yes. Now it's clear.
Great, let's practice. So I'm going to ask you a few questions and you're going to answer me, and we're going to make some for different formulae, and that's going to be a good practice for you. So we have magnesium and chlorine this time, a different set of elements. So what is the valency or the charge on magnesium?
+2.
Which means magnesium is going to lose how many electrons?
2.
Great. And what about chlorine?
It has a -1 charge, so we
Negative
write
one. Right. So how many electrons is it gaining?
-2.
No,
1. Sorry. 1.
1.
1. 1.
Minus means the electrons are gained. 1 means the number of electrons gained are 1. Plus means the electrons are lost. 2 means the number of electrons lost were 2. It's as simple as that. Okay? So remember,
Yes.
the plus sign means electrons are lost while we were making the ionic compound. The minus sign means the electron were gained. 2 means 2 electrons are lost, 3 means 3 electrons are lost. Whether it's written with a plus sign or with minus sign, number represents the number of electrons lost or gained. Plus means electron lost, negative means electron gained, right? So now we're going to reverse the numbers and we're going to write the numbers as subscript on different elements. So we're going to wind up with what?
MgCl2.
MgCl2, perfect. Now you already know we never write 1 as a subscript, so it's not Mg1Cl2, simply speaking, it's MgCl2. Great, right?
Yes. Yes.
Perfect. Now, do you have periodic table open in front of you? If not, please,
Um.
you can open it up. Take your time. When you're ready, let me know.
Yes, sir. I opened it.
Okay, okay. So you can see group 2 in front of you as beryllium, magnesium, calcium. But if you look at the periodic table, you're going to also find in the same list as strontium. All right. So we're going to combine strontium with
Yes.
sulfur this time. I'm taking different elements. I'm going out of this diagram. So this diagram is just an idea. Anything beneath it will have the same numbers. So strontium will have the same valency as calcium or magnesium or beryllium, any of the metals above it. So the charge on strontium is going to be
+2.
perfect, and the charge on sulfur is going to be sulfur is a part of this diagram, so this should be easy. Light green,
-2.
-2. So let's cross multiply these and write them as subscripts, but without the signs. So the answer would be, what are we going to write beneath SR?
2.
Good. What are we going to write beneath S?
2.
Perfect. Now, here comes another thing that we haven't been doing before. This is known as simplification. Since both the numbers are divisible by one another, we are going to divide them by the similar number, and we're going to end up as SR1 and S1. Since we don't write ones, we're going to convert it into SRS. That's why we write it like this.
Yeah, that's what I was thinking.
Great. So now you know. Now you know why some ionic compounds don't have any numbers at their bottom. Why? Because the numbers probably have been cancelled or simplified because of the simplification step. Make sense?
Yes.
Great. If that makes sense, we can always practice one more question like this one. So there is an element aluminum and it can easily react with nitrogen. The charge on aluminum would be
+3.
and the charge on nitrogen is going to be
-3.
perfect. So if we cross multiply these charges, we're gonna get, you may tell me the final product. If you require to go through the step of simplification, please go through it and tell me the final answer.
ALN, because it will be cancelled out.
ALN. Perfect, because they would either be cancelled out or simplified. You can use both terms. Now you know how to make formulae for ionic compounds. But it's not as simple as it seems for polyatomic ions, because we have studied polyatomic ions in the previous examples. So let's erase the simple examples. We're done with the easy questions. Let's move on to the difficult ones. So I'm gonna erase all of it, and we're going to start off with polyatomic ions. Now remember, there are just 7 or 6 polyatomic ions that we have in our course. So we're gonna stick to those. So let's suppose that we have potassium and we have carbonate as the polyatomic ion. Now, polyatomic ions have specific charges and they do not change. We need to memorize them along with the charges. So carbonate has CO3 formula. It has -2 charge and that never changes, stays as -2. Would be the charge on potassium? K.
+1.
We can simply write positive. If we're gonna move them, what would be the answer?
K2CO3.
Right, K2CO3. Since there was one up top, so there would be no changes. It's easy. Let me take a difficult example. Okay. Right. Aluminum with sulfate, SO4 -2. What's the charge in aluminum?
It's +3.
3 plus. So, reversing
So
them,
it becomes aluminium 2, and we're going to write brackets and then sulfur
Perfect.
3.
You already know that we have sulfatine and then 3. So this is Al2SO4 and we don't call it T. It's called thrice. After the brackets, the numbers are not named in the same way. 2 becomes twice, 3 becomes thrice. So it's Al2. It's not Al twice, it's Al2, but SO4 thrice. So Al2SO4 thrice. That's how we pronounce it. When we are answering our teacher orally out loud, so that's how we pronounce it. And now you understand that the brackets are always put with the polyatomic ion if the number is greater than 1. If the number is 1, we do not need to put the brackets like we did in the previous question, but a new set of rules, we are going to put brackets along with the uh, numbers that are greater than 1 in subscripts for polyatomic ions. You can also make a compound out of 2 polyatomic ions. So we're going to consider 2 polyatomic ions, NH positive 4 and um, phosphate PO4 negative 3. So what do you think the answer is going to be? If I cross multiply these numbers, what will be the answer? Go ahead.
It would be NH4 in brackets
Perfect.
and 3 outside that, and then uh, it would be PO4.
It would be PO4. This is NH4 thrice PO4, which is ammonium phosphate. Easy peasy,
Yes.
right? I hope it's as easy peasy for me as it is for you. Actually, I said
Yes.
the opposite. I hope it's as easy peasy for you as it is for me. Okay, okay, I'm gonna clear all of this up. Now, now the book actually segregates the covalent bonding, but they don't give you a separate formula. So I'm gonna give you a formula for covalent bonding. Okay, now next up is covalent bonding. Remember one thing, one very important thing, that covalent bonding is made up of non-metals only, which means none of the blues are going to participate. The dark greens one are noble gases, they don't react at all. So it's all between yellows and light greens. Okay. So if I talk about those covalent compounds, now covalent compounds do not lose or gain electrons. So how do we deal with their numbers? We simply have the formula of 8 minus group number. This is the formula by which we're going to get the numbers out of it. So this is group number 1, this is group number 2, this is group number 3, this one is group number 4. So if you go with the formula 8 minus group number, so for the group of carbon, 8 minus 4 is equal to, so
4.
that's the number for carbon. What about for the group of nitrogen? 8 minus 5
It
is
will
equal to,
be minus 5, and it will be 3.
right? For oxygen, 8 minus 6 is equal to,
2.
for fluorine's group, halogens I mean,
It will be 1.
and this would definitely be 0. But since that is not included. Now, what if the elements react? For example, carbon reacts with oxygen. What would be the number up top on carbon? It would be,
4.
now this time we do not write numbers. Why? Because they do not lose any electrons. They do not gain any electrons. They only share electrons. Now, how many electrons is oxygen going to share as per the number up top?
2.
So let's cross multiply them. What would be the answer then?
C2O4.
Can we simplify it?
Yes.
And the answer would become,
C2O2.
huh? CO2.
No, yeah, CO2.
C1O2, and basically we don't write 1. So there you go. Now you know how do we get the formula of carbon dioxide. Make sense?
Yes. But sir,
Great.
could you please repeat the last part?
We actually simplified it. It's C1O2 because 2 ones are 2, 2 twos are 4. And since we
Right.
don't write 1, it would become CO2. Easy enough.
Okay.
Some rules
Yes.
are same in ionic compounds and covalent compounds. We have been simplifying in ionic compounds. We're still simplifying in covalent compounds. We don't write the ones in ionic compounds. We don't write the ones either in covalent compounds. Those rules are pretty much the same. In fact, the cross multiplication of the numbers is even the same. It's just that they don't have any sign. Why? Because they do not lose or gain electrons. Let's try something different. Okay, phosphorus is going to react with oxygen. So the number on top of phosphorus is
3 and 2 on oxygen.
cross
So
multiplying.
it
The
would
answer would be
be P2 O3.
great. Easy, right?
Yes.
Okay. Carbon can react with chlorine. The number on top of carbon would be
4
number
and
on top
1
of chlorine, 1.
1.
Cross multiplying, the answer would be
C Cl4.
there you go. Now you know. Now you know how to deal with covalent compounds and ionic compounds separately. Remember, this formula was slightly different from covalent compounds. I used group number first and 8 after. That's how I came up with plus and minus signs, right?
Oh, right.
Now you
Okay.
understand what those numbers and what those formulae meant. Now this
Yeah.
all makes much more sense, right?
Yes.
Great, great. I'll send you the recording. You can repeat it after if you ever have a confusion, or you can always ask me what to do. So this is pretty much all we need to do in case of formulae for ionic compounds or formulae for covalent compounds. The similar examples have been used in the book. All right. I never use these formulas as it is. I use them a little bit differently. They've already given the numbers, but I usually tend to put signs with the numbers in case of ionic compounds. And in case of covalent, we do not need numbers with metals. Since there are no metals included in covalent bonding, we only need non-metals and those even without the plus or minus sign. Now you understand what I mean from that. Good enough, right?
Yes.
But remember, chemistry is a subject of exceptions. So you may see many formulae not following the same rules. Do not get confused. There are many compounds or formulae that do not follow the rules. So there are always exceptions in chemistry. Okay,
Right.
so let's move on. Next up, naming chemical compounds. So actually, there are a lot of rules in here for chemical compounds. What I usually tell my students is that you can bifurcate these rules. All of these rules up top, the first four rules are for ionic compounds, right? And this rule is for covalent compound. The last rule is for covalent compound. So the ionic compounds are explained in first four rules, and the covalent compound is only explained in one rule. Okay. So let's go through these rules
Yes.
quickly so that you don't have a problem naming compounds. Okay. First things first, there are some compounds for which we don't even know how the names are given, and we're still using those names. For example, water. H2O is water. Nobody knew who gave the name water, but we still use it. We don't use any other scientific name. Ammonia for NH3, methane for CH4, we still use those names. We don't know who gave the name. Even if we do, we don't change those names. Apart from that, the rules are for the generic naming for ionic compounds. Since ionic compounds is made up of a metal and a non-metal, we always name the metal first. All right. So if it is made up of sodium and chlorine, since sodium is a metal, so we're always going to write sodium first, right? For
Right,
example,
sir.
if you're familiar with the most common Muslim names or Pakistani names, what do? Our names come first, and the surname or the last name comes after. There's a
Yes.
trend we do that, how we write the names. So we do have rules in place for ionic and covalent compound naming. So the metals are named first and non-metals are after. Okay. So where metal can form more than one ion, and in this case, we have this iron example, it can form a +2 ion, it can form a +3 ion. So it can form a chloride with iron 2 chloride and iron 3 chloride. What do we mean from it? The name indicates which ion is present. So this indicates it has lost 2 electrons. This indicates it has lost 3 electrons. So we get to know what kind of ion it is forming. What are we doing? Right after the name of the metal, we are using parenthesis bracket and we are using Roman numerals to write the number of electrons it lost. Easy enough? So iron 2 or iron 3. Remember, parentheses are small brackets and Roman numerals. We don't write 2 like this. That's not the way it is. Clear enough?
Right.
This
Yes.
usually works with transition elements given in the center of the periodic table, which we did not practice uh, for the examples we just did. Why? Because we usually don't know what kind of ion they're going to form. Whatever ion is given in the exams, and now you know how they're going to tell you what kind of ion is present. So what if they tell you that it is iron 2? Now you know that if iron 2 is going to combine with fluorine, what kind of formula it would give you. Now you can practice. It is
Yes.
FeCl2. So that's why I did
Yes.
not go with this example previously because I knew that the questions are usually asking the exams with the name. And once we study the rules for the name, you'd automatically understand how to form the formula. Easy enough? I don't think we need to practice
Yes.
this, right?
Yes. Yes.
Great, great. Moving on. Third rule, compounds may contain only 2 elements. Now, since we have polyatomic ions, it changes everything in ionic compounds. Now, ionic compounds can be formed only with 2 different elements, like we have an example over here. Like one of the elements is metal, iron in this case, and one of them is fluorine, this one. So there are just 2 elements. If the compounds have 2 elements, the names end in IDE, which means the name of the non-metal is always changed. Now, this is NaCl. It was supposed to be sodium chlorine, but it's not chlorine. We intentionally changed the name with IDE ending. It's sodium chloride, not chlorine. This is CaBr2. This was supposed to be calcium bromine, but it's not bromine since we replaced it with IDE and it's calcium bromide. This was supposed to be magnesium nitrogen. It's not magnesium nitrogen. Magnesium stays the same. We don't do anything to the name of the metal. Nitrogen becomes nitride. We intentionally replaced the last part of non-metal with IDE and it became nitrogen nitride. Make sense?
Yes, sir.
And let me tell you that you can notice the same thing if you go a few pages back to the table of polyatomic ions. See something over here? You might not have noticed over here, or if you noticed, we never spoke about it because we were quickly going through it. It's not hydrogen, it's hydride, not chlorine, chloride, not bromine, bromide, not iodine, iodide, not oxygen, oxide, not sulfur, sulfide, not nitrogen, nitride. So you can see we have changed the name of every single non-metallic ion in there with IDE. Whatever the name was, be it oxygen or nitrogen, be it sulfur or bromine, it is always ending in IDE. Make sense?
Yes, sir.
Now you may connect the dots of this huge table with the rules of naming we have on a very different page. Okay, getting back to the original page where we were reading the names. So now you know what do we do with 2 elements. The only exception to this rule are hydroxides. Hydroxide is a polyatomic ion. Even the ion consists of 2 different elements, oxygen and hydrogen, but the name still ends in IDE. That's the only exception to the name. All other polyatomic ions have a names that end in ATE. Carbonate, CO3, nitrate, NO3, sulfate, SO4, ethanoate, CH3COO. So the polyatomic ions have the names ending in ATE to keep them different from the simple ionic compounds that only consist 2 elements, a metal and a non-metal, right? This differentiation is done so that as soon as you read the name, you will know whether it consists of a polyatomic ion or a simple ion. If it's IDE, that's a simple ion. If it's ATE, it's a polyatomic ion. As easy as that. Make sense?
Yes, sir. Sir,
Yeah?
could you tell the valency for ethanoid?
Yeah, this one is CH3. Sorry, that's not a part of that table. And I really admire your vigilance. This is CH3COO negative. And that wasn't a part of the table. This actually is a part of organic chemistry. So basically chapter number 10.
Yes.
Yeah,
Thank you, sir.
welcome. So moving on, we're done with the naming of ionic compounds. So we have only 1 point left to name covalent compounds. Now in covalent compounds, actually, we don't have any ions. There are no positive ions, there are no negative ions. So what do? We use prefixes, number prefixes, means telling how many atoms for a specific element were there. Now the prefixes are like this, since the book does not discuss the prefixes separately, so we use mono for 1, we use di for 2, we use tri for 3, we use tetra for 4, we use penta for 5, and we use hexa for 6. This is for the number of atoms there are in a compound. Now, the rules are pretty simple. They're not mentioned over here, so I'm going to mention it for you. For the first element, if the number of atoms is 1, you never use the prefix mono. All right, for the first element alone. For example, this will not be monocarbon monoxide. It's just carbon monoxide. Make sense?
Right. Yes.
This one is carbon dioxide, not monocarbon dioxide. Since the first element has only one atom, it is going to be carbon dioxide. This is going to be nitrogen dioxide. This is going to be sulfur dioxide. I hope that makes sense. Sulfur trioxide. Okay. Only in the case if the first element does not have one atom, it has more than one, you need to use prefixes for all the atoms. Okay, let's go with this one. This one is dinitrogen tetroxide. Make sense?
Right. Yes.
So, since, Alhamdulillah, since I've already named these, so for practice, let's name something differently. So, what do you think is the name of this one?
Dinitrogen trioxide.
Now, one rule that is similar in covalent compounds that was there in ionic compounds is that the element on the right-hand side is also named as IDE. Only the element at the left-hand side has to keep the same name. So nitrogen is same and oxygen is converted into oxide, and yes, you're perfect. That is dinitrogen trioxide. Okay, let's do one more example. Okay, it's a similar one, by the way.
Um, di phosphorus
Phosphorus, right?
dioxide.
Perfect. Let's try this one.
Diphosphorus pentoxide.
Perfect. Let's try this one.
Phosphorus pentafluoride.
Perfect. This one.
Sulfur hexachloride.
Right. Now you know. It was easy, right? If you know the rules,
Yeah.
there are not many rules. There are simple 2 to 3 rules that you need to follow. And if you know the prefixes, you will not be able to go with any wrong names. Okay?
Yes.
Now the name for important mineral acids are systematic, but they're best simply learned at this stage. For example, sulfuric acid, hydrochloric acid, nitric acid. So the names are to be learned in the way they are. All right. There are two important oxidizing agents that contain the specific negative ions. They're named. So we remember potassium manganate 7 as KMNO4 and potassium dichromate 6 as K2Cr2O7. These are the names that you might need to cram as they are without any systematics. Okay. Just
Right,
like we
sir.
remember for water or for ammonia or for methane, since those names are trivial and they're still going on, these names have a patron, but we don't understand the patron at this stage and we simply memorize them. This also finishes 3.5 for us. So we're left with the last topic, 3.6,
Yes,
metals,
sir.
alloys, and crystals.